Okay, now we are going to take what you learned about sampling distributions to estimate single population parameters. But up to this point, we've been operating under the assumption that we know what the population mean is. However, that's rarely the case. So, if you ever hold a managerial position, chances are you will need to estimate population parameters like the mean in decision making. Chances are you will also need to evaluate estimates that you receive from vendors or other business partners. Essentially, you will need to gather information from a sample and then use that information to make a statement about the population from which your sample was chosen. So in statistics and in the real world, we often assume a sample or we often use a sample as an estimate for a population. But the question is, how good of an estimate is the sample providing us? Well, we can apply our knowledge of the standard error and finding z-scores in the unit normal table to estimating the value of the true population mean and understanding how much error we can expect when it comes to our estimate of the population mean. For our purposes, we're going to assume that we have a normal sampling distribution, which is often the case, and we're going to assume that we know the population standard deviation. There are certainly situations when this is not the case, when we do not know the population standard deviation, and the textbook, if you have it, covers some of them. However, understanding the most basic situation for estimating single population parameters will help you understand more complex situations when we do not have a normal sampling distribution or when we do not know the population standard deviation. Now, when you don't know the population standard deviation, you essentially estimate it using the sample standard deviation, and you use the same processes that I'm going to show you, only you're going to be using T statistics instead of Z statistics if you do not know the population standard deviation. But again, for our purposes, I'm going to focus on scenarios where we know the population standard deviation, we have a normal sampling distribution, and we're using the unit normal table and z-scores. So first I'm going to talk about the margin of error, which is the foundation for confidence intervals. And confidence intervals just give you a range of means that you expect your population mean to fall within. Then I'll just show you a couple of real-world examples of confidence intervals. And then I'll do several example problems showing you how to compute confidence intervals and helping you understand what confidence intervals actually tell you. So the margin of error is essentially telling us how far off we expect our estimate of the population mean to be. Now remember, the standard error tells us the difference to expect between the sample mean and the population mean due to random sampling error. But we are now operating under the assumption that we do not know what the population mean is. However, we can use the standard error to help us determine the range of possible mean values that we expect based on our desired level of confidence. And common desired levels of confidence are 90% level of confidence, 95% level of confidence, and a 99% level of confidence. So the desired level of confidence leads us to a z-score based on taking your alpha level. And alpha is equal to 1 minus the desired level of confidence divided by 100. So if we have a situation where we have a 90% confidence level, then we would find alpha by taking 1 minus 90 divided by 100, or 1 minus 0.90, and our alpha level would be 0.10. So when you see this little formula for the margin of error, z, this little subscript, alpha, if we had a 90% confidence level, this would be z for an alpha of 0.10. And then we would just take that z that we find in our table and multiply it by the standard error to get our margin of error. If we had a 95% confidence level, then we would take 1 minus 95 divided by 100, which becomes 1 minus 0.95, and our alpha level would be 0.05. So for a 95% confidence level, you could replace this little alpha with a 0.05 in the formula. For a 99% confidence level, we would have, to find alpha, 1 minus 99 divided by 100, which would be 1 minus 0.99, and we'd get 0.01. That would be our alpha that you would replace here in the formula if we had a 99% confidence level. So once we find the alpha, we use that to locate the z-score. And then we multiply that z-score by the standard error to estimate the range of expected population mean values within whatever level of confidence that was used to determine alpha and the z-score. So the confidence interval for the mean is the interval estimate around a sample mean that provides us with a range of where we think the true population mean lies. So the confidence interval tells us, or the confidence level tells us how confident we are that the true population mean falls within the confidence interval. So if we have a 95% confidence level, then we're 95% confident that the true population mean falls within the confidence interval that we found. So to find the estimated range of true population means, or the true population mean, or the confidence interval, we take the sample mean and subtract the margin of error to get the low end of the estimate, or the lower limit of the estimate. Then we take the sample mean and add the margin of error to get the high end of the estimate, or the upper limit of the estimate. Now, just remember, this estimated range of the true population mean, or the confidence interval, does not always include the true population mean, but we are pretty confident, based on the level of confidence, that the true population mean is included in the confidence interval. Okay, enough about abstract concepts. Let's go ahead and take a look at some examples. So here's an example looking at a 90% confidence interval when we know that we have a sample size of 100, a sample mean of 10 that we're working with, the population standard deviation is 20, and based on this information I know my standard error is 2 because the standard error is equal to the standard deviation divided by the square root of my sample size. 20 divided by the square root of 100, or 20 divided by 10, is 2. So if the confidence level is 90%, we're essentially looking for the two means that separate the middle 90% of the distribution from the rest of the distribution. And when we look at this, we are 90% confident that the sample mean will fall, or the population mean will fall between the two values that we end up finding right here. For now, pretend you don't know any of this because I haven't found it yet. All right, so we identified when you have a 90% confidence level that your alpha level is 0.10. So you take 1 minus 90 divided by 100 becomes 1 minus 0.90. You get an alpha level of 0.10. Now this alpha level, this proportion of the distribution that we are going to use to find our z-scores is going to be split. So we're looking at the two scores that represent the middle 90% of the distribution. So we're left with 10% of the distribution, or an alpha of 0.10. But that 10% needs to be divided into the two tails. So you take that alpha, 0.10, divide it by 2, and you get 0.05. So essentially we're saying that this represents the middle 90% of the distribution, and then the remaining 10% is split up into two tails. So we have the 5% on the high end and the 5% remaining on the low end. So once you have your alpha level and you split it into the two tails, you know that now we're going to be looking for 0.05 in the tail to identify the z-score for our margin of error. So I'll show you how to find that. So you'll go to your unit normal table. You'll find 0.05 proportion in the tail. And 0.05 isn't there exactly, but you'll look for the one that's just above it and the one that's just below it. And you see that they're both the exact same distance from 0.05. They're both 0.0005 away from 0.05. So you will say, okay, it's a toss-up between these two z-scores, 1.64 and 1.65. Well, because we want to err on the side of caution, we're going to go with the larger z-score because that'll give us a slightly larger margin of error, and we want to be careful. All right, so 1.65 is the z-score associated with an alpha level of 0.10. So that z-score that corresponds to 0.05 in the tail. Remember 0.05, your alpha level divided by 2 because we're looking in two tails is 1.65. So now we use that to calculate our margin of error. So z, alpha level of 0.10, is 1.65 times the standard error, which is 2. You get a margin error of 3.3. So you use that margin of error to figure out the confidence interval. So we take the sample mean, which is 10 in this case, and then we're going to add the margin of error to find the high end of the estimate, or the upper limit. Then we're going to take the sample mean and subtract that margin of error to find the lower end of our estimate, or the lower limit. So that essentially means, right, we just replace sample mean with what the sample mean is, 10, plus or minus the margin of error, 3.3. So then here, for the low end, we have 10, the sample mean, minus the margin of error, 3.3. We get 6.7. The high end, 10 plus 3.3 to get 13.3. So our confidence interval is 6.7 to 13.3. And a mean of 13.3 corresponds to a z-score of positive 1.65, and a mean of 6.7 corresponds to a z-score of negative 1.65. So we are 90% confident that the true population mean is between 6.7 and 13.3. Now let's look to see what happens when we have a 95% confidence level. So let's still assume that we have a sample size of 100 with a population standard deviation of 20, which results in a standard error of 2, and we're also looking at a sample mean of 10. If the confidence level is 95%, we're essentially looking for the middle 95% of all possible sample means, and we're 95% confident that the population mean will fall between these two sample means. So, with a confidence level of 95%, our alpha level is 0.05. Remember, 1 minus 95 divided by 100 would be 1 minus 0.95, which would give us 0.05. And just like last time, we need to take that alpha level and split it into the two tails that are remaining. This represents the middle 95%. Then this would be 0.05 divided by 2, 0.025, or 2.5% would be here, and 2.5% in this tail. So now we're going to look for 0.025 in the tail in our unit normal table to find which z-score is at that location. So we look for 0.025 in the unit normal table. Oh, yay! We have that exact value right here in the tail. That gives us a z-score of 1.96. So then we take that 1.96 as our z-score at an alpha level of 0.05 to find our margin of error. Take that 1.96, multiply it by the standard error of 2, and your margin of error is 3.92. Then we take that margin of error and we add it to our mean, and then we subtract it from our mean to find our high and our low end. So our sample mean is 10, 10 plus or minus our margin of error of 3.92. So for the lower limit, or the low end of our confidence interval, we take 10, subtract the margin of error. 10 minus 3.92, we get 6.08. To find the high end of our confidence interval, or the upper limit, we take 10 and add 3.92, the margin of error, and we get 13.92. So if we visualize this in a graph, we've got the 6.08 that represents the mean with a z-score of negative 1.96, and our 13.92, which is the sample mean represented by a z-score of 1.96, and we are 95% confident that the true population mean is between 6.08 and 13.92. Now notice, with a higher confidence level, we are more confident that the true population mean falls between these estimated values. But the interval is wider and is therefore less precise than a situation where we have a smaller confidence level. We're less confident that the population mean falls between these two values, but we have a more precise range. Now notice, when we have a 99% confidence level, we have an even larger range, but we are more confident that the sample mean, or the population mean, falls within this confidence interval. So we're still assuming that we have a sample size of 100, sample mean of 10, standard deviation of 20, and a standard error of 2, 20 divided by 10. But now we're working with a 99% confidence level. And the alpha level for a 99% confidence level is 0.01. Remember, 1 minus 99 divided by 100 would be 1 minus 0.99, and that would give you 0.01. So we take that alpha level, right, and we divide it in 2, and we're looking for 0.005 in the tail in the table. So this represents the middle 99% of the distribution, and then we take that remaining 1% and we essentially split it between those two tails. And so we're going to go to the table and find 0.005 in the tail and figure out what z-score that corresponds to so that we can calculate our margin of error. So we go to our unit normal table. We're looking for 0.005 in the tail. So, all right, it's a toss-up between this one, and they're both the same exact distance from 0.005. They're both 0.0001 points away from 0.005. You go with the larger z-score. That's where I got 2.58 for the calculation in my margin of error. So the z-score with an alpha level of 0.01 is 2.58. 2.58 times my standard error of 2 gives me 5.16. And then I take that margin of error, I take my sample mean and subtract it, then take my sample mean and add it to find my lower and upper limits of my confidence interval. So I take my sample mean of 10 minus my margin of error, 5.16, to get 4.84. Take my sample mean plus my margin of error, 5.16, to get 15.16. So I am 99% confident that the true population mean falls between 4.84 and 15.16. Again, an even wider confidence interval than with a 90 or 95% confidence level, but even though it's less precise, we're more confident that our population mean falls between those two values. And just again, sample mean of 15.16 has a z-score of 2.58. Sample mean of 4.84 would have a z-score of negative 2.58. So now just a couple of real-world examples of confidence intervals that you may see in everyday life.
Okay, Google, how long do koalas sleep each day?
On average, a koala sleeps somewhere between 18 and 22 hours every day.
That's the life.
So chances are researchers did not measure every koala. They probably took a sample of koalas to estimate how long all koalas sleep, and 18 to 22 hours is probably the 95% confidence interval. That's typically what's used, is 95%. Now let's look at a Gallup poll examining what Americans think the biggest issues for working women are. Okay, so if you look at this poll, it says, okay, 39% of all Americans think that equal pay or fair pay is the biggest and most important issue facing working women in this country today, and 42% of working women think that equal pay or fair pay is the most important issue facing working women in this country today. Well, they didn't ask me, and they probably didn't ask you, so this is not an accurate, 100% accurate representation of the population because they didn't ask everybody. So when you look at Gallup polls, and they're pretty good about reporting what's actually going on, if you go down to the bottom here, you will see that for results based on the total sample of national adults, the margin of sampling error is plus or minus 4 percentage points at the 95% confidence level. So what this is really saying is that we're pretty confident with 95% confidence that 39 plus or minus 4, or between 35 and 43% of Americans think equal pay is the most important issue for working women. Now, if you look down here, it gives you the confidence interval. So results based on the total sample of, there's only 233 working women in this sample, but results based on that have a margin of sampling error that's plus or minus 8 percentage points at the 95% confidence level. So 42 plus or minus 8. So it's actually estimated that between 34% and 50% of working women think equal pay is the most important issue for women. Now, these are probably examples of a situation where you would not have the population standard deviation, so you would use the sample standard deviation to estimate it. But that's beyond the scope of this class, and understanding sampling or confidence intervals and margin of error will help you understand that kind of stuff in the real world. So now I'm going to do some example problems where I'm actually going to write everything out for you and draw the distributions and all that, and it's not just up on the screen. And I encourage you to try the gold problems on your own before you watch the answers. All right, now let's work through some handwritten example problems for estimating single population parameters, or in other words, finding the margin of error and confidence intervals. Okay, so if we're looking at a sample of 32 customers from the home shopping network, and that sample spent an average of $129.20 on their order, and you know that the standard deviation for the amount spent per order in the population of home shopping network customers is $40.60, what is the 90% confidence interval for the mean of all customers of the home shopping network? So in other words, we want to have some sort of range of values that we're 90% confident that the population mean falls into. All right, so the first thing that we need to identify is our alpha to figure out what type of z-score we're looking for. So if I draw this out, we know we're looking for the middle 90% of the distribution. So P equals 0.90. And we know that our alpha is equal to 1 minus 90 divided by 100, right? 1 minus our confidence level divided by 100. So this becomes 1 minus 0.90. We know that we're left with 10% of the distribution if we're looking at the middle 90%. And we have to take that 10% of the distribution and then we have to divide it into those two tails to get 0.05. So we've got P equals 0.05 in each tail. So now we know that we need to find the z-score associated with 0.05 in the tail. So the z with an alpha level of 0.10, and we split that 0.10 into two tails, so we're looking for 0.05 in the tail to find our z-score. So go to our unit normal table, 0.05 in the tail. So it's a toss-up between these two. They're both the same distance from 0.05, but we go with the larger z-score, so 1.65. So 1.65. Then to find our margin of error, we take that z-score and we multiply it by our standard error. Well, our standard error, because I already know my z-score is 1.65. I don't know what my standard error is. It's equal to the standard deviation divided by the square root of the sample size. And that gives me, let's see, the standard deviation is 40.6. The sample size is 32. So this becomes 40.6. Well, the square root of 32 is 5.657. And I end up with a standard error of 7.177. So I plug that in here. I'm going to go ahead and erase my pretty picture. It's because I didn't leave myself enough room here. And so I know that my margin of error is equal to my z-score times my standard error. And so 1.65 times 7.171 gives me 11.842. That is my margin of error. So then I take that margin of error, I add it to my sample mean to find the upper limit of my confidence interval, and then I subtract it from my sample mean to find the lower limit of my confidence interval. So confidence interval is equal to the sample mean plus or minus 1 margin of error. And let's go ahead and get rid of the 1 and just leave it as an E. So what this becomes is, so my sample mean 129.2 plus or minus my error 11.842. So 129.2 plus 11.842 is equal to 141.042. I'm just going to go ahead and round that to 0.4 since we're working with dollars. And then 129.2 minus 11.842 is equal to 117.358 or 117.36. So, our 95% confidence interval ranges from 117.36 to 141.04. And I am 90% confident that the true population mean of spending per home shopping network customer is between $117.36 and $141.04. Now I'll say that again because the interpretation of this is very important and I just don't have room to write it out. So we are 90% confident because our confidence interval is based on a 90% confidence level. So we're 90% confident that the true population mean of spending per home shopping network customer is between $117.36 and $141.04. All right, now let's do the next one. So let's say we take a different sample of 32 customers from the home shopping network, and we know that they spent an average of $132 on their order, and we want to know what is the 90% confidence interval for this sample. So with different samples, you're going to have different confidence intervals. But in this case, our margin of error, or our E, is the same because we are still working with the same confidence level. So we still have the same z-score, right? And the same standard error because we're still working with the same sample size from the same population deviation, standard deviation. So our margin of error is still going to be equal to 11.842. All right, but now our confidence interval is going to be based on this new sample mean. So now our confidence interval is equal to, so our new sample mean plus or minus the margin of error, which is 132 plus and minus 11.842. So if we take our sample mean and add 11.842, we have 132 plus 11.842, which gives us a high end or the high upper limit of our confidence interval of 143.842 or $143.84. And then the low end of our confidence interval, or our lower limit, 132, the sample mean, minus the margin of error, is equal to 120.158 or $120.16. So we are, based on this sample mean, we are 90% confident that the true population mean of spending per home shopping network customer is between $120.16 and $143.84. So I'm going to go ahead and redraw my distribution. And I'm going to go ahead and mark this in blue. All right, so we've got our normal distribution, and we've got our mean for group 1 and our mean for group 2. So now here in the middle, if we drew these two different distributions, this first example had a mean of 129.2. This second example had a mean of 132. And the first confidence interval was 117.36 to 141.04. Now, in both cases, this represents the mean value that separates the bottom 5% from the rest of the distribution, and this from the top 10% of all sample means from the rest of the distribution. And in this second example, we had a situation that looked like this. And in both cases, based on whatever sample mean we're looking at, we came up with the low end is the sample mean that separates the bottom or the least likely bottom of the 5% of the distribution, and then the upper limit separates the top 5% of the distribution or the unlikely high means from the rest of the distribution. All right, so just wanted to point out that both of these samples have the same margin of error, right? Because the sample size and population standard deviation are the same for both, and we're looking at a 90% confidence interval. However, it's important to realize that each sample taken from the population will probably have a different sample mean due to sampling error. So each mean is going to result in a different confidence level or different confidence interval, even if the sample size is the same. So what the confidence level of 90% tells you is that you can expect 90% of all sample means you could possibly select from the population to result in a confidence interval that includes the true population mean. So take a look at this. So let's say that we had 10 different samples with 10 different sample means. We're still looking at a margin of error of 11.842. because we're still using the same population standard deviation and the same sample size and the same confidence level. But you're going to have a different lower and upper limit for all of these samples. So these two we've already done, right? So we had the sample mean plus 11.842 gave you the upper limit, sample mean minus 11.842 for the lower limit. Then like if we scroll down to this one, if we had a sample mean of 128.20, add the margin of error to get the upper limit, subtract the margin of error to get the lower limit. So just hypothetically, we're looking at a situation where we took 10 different sample means and we constructed 10 different 90% confidence intervals. So these last two columns represent the 90% confidence interval. Well, let's say that we mysteriously found out that the true population mean was 125. And looking at this data, we see that 9 out of 10 confidence intervals include that population mean of 125. Well, that would not be a surprise because based on the very definition of looking at a 90% confidence interval, we would expect that 90% or 9 out of 10 samples would produce a confidence interval that includes the true population mean. So a lot of people will say, oh, well, if I have a 90% confidence interval, that means there's a 90% chance that I have a true population mean in here. But that's not wholly accurate. What you're saying is that you're 90% confident that the true population mean falls in there, which means that there's a 90% chance that any given sample mean that you take would produce a confidence interval that included the population mean. So it's kind of a nuanced difference, but I wanted to show you this just to demonstrate what does it mean when we say we have a 90% confidence level. Well, we would be confident that if we took 10 samples, 9 out of 10 of those samples would produce a confidence interval that includes the true population mean. Okay, so now I want you to pause this lecture and try these problems out on your own before watching me go through the solutions. All right. Okay, so we're still working with the sample of 32 customers, and we're still working with those two different sample means that we looked at before. Only now we're working with a 95% confidence interval instead of a 90% confidence interval. So when we go to figure out what our alpha level is, we're going to have 1 minus 95 divided by 100, which is 1 minus 0.95, which gives us an alpha level of 0.05. So we're essentially looking for the sample means that represent the middle 95% of the distribution, or P equals 0.95. And we take what's left, 0.05, or 5% of the distribution, and we split it in half, and we get 0.025, and we know that we are looking for P of 0.025 in the tail to find our z-score. So these pieces right here. So I'm going to go ahead and write my margin of error formula as z alpha level of 0.05 times my standard error. All right, so let's figure out what is z for an alpha level of 0.05. Now don't get tripped up when you see z 0.05, right? You don't even have to write that if it doesn't help you, because remember, we're taking that alpha level and we're splitting it. So we're looking for p of 0.025 in the tail to find our z-score. All right, 0.025. Oh, I passed it. Oh, remember? Right there it is, right? It's the exact number that's actually in the table for proportion in the tail, which is rare. Usually you have to kind of like look for the closest one, and that gives us a z-score of 1.96. So 1.96 is the z-score of interest. So if we sketch our distribution here, z of 0 in the middle, and we're eventually going to find the value, the mean at a score of 1.96, and the mean for negative 1.96. But for now, we're just talking about the margin of error. So we're just going to use 1.96, not the negative version, because eventually we're going to subtract the margin of error from the mean to find the negative version. Okay, so the standard error, we already found the standard error. So remember, it's 7.177. Oh, I just caught something. Totally messed that up there. That's a 7, not a 1. Okay. So 7.177 is what we put here. Standard error hasn't changed because we're still working with the same standard deviation for the population and the same sample size. So 1.96 times 7.177 gives you 14.067. And as expected, that margin of error is larger than the margin of error when we have a confidence level of 90% because we're going to have a wider confidence interval because we want to be more confident that the population mean would actually fall into it. All right, so here's E. So now we need to find our confidence interval. I'm going to abbreviate that CI by taking our sample mean plus or minus our margin of error, which is the same in this case of saying 129.2 plus or minus 14.067. So I'm going to go ahead and find my low end first this time. So 129.2 minus 14.067 gives me a value of 115.133 or 115.133. $115.13. I always have you round to the thousands place, but when we're doing dollar figures, if you round to the hundreds, that's fine because that's typically how dollars are represented. All right, 129.2 plus, so the sample mean plus the margin of error, 14.067, and you end up with 143.267 or $143.27. So let's go ahead and fill those in our table here, or our graph. So 115.13 and 143.27. So 143.27 represents the sample mean with a z-score of 1.96. 115.13 represents the sample mean with a z-score of negative 1.96. So we are 95% confident that the population mean of spending per home shopping network customer is between $115.13 and $143.27. Now again, notice that the 95% confidence interval is wider than the 90% confidence interval. 117.36 to 141.04 versus 115.13 to 142 or 143.27. So it's wider even though we're using the same sample mean and population because we have a larger confidence level. So we are more confident that we caught the true population mean. So, of course, the confidence interval needs to be wider so that we're more confident. All right, the next one. The margin of error is going to be the exact same as the previous example because we're using the same confidence level and we have the same standard error because we have the same sample size and standard deviation in the population. So margin of error is still equal to 14.067. Only now we're working with a sample mean of 132. So our confidence interval is going to be represented by still the sample mean plus or minus error, but now it's 132 plus or minus 14.067. So if we find the lower limit of our confidence interval, 132 minus 14.067, we end up with 117.933 or $117.93. And then the upper limit or the high end of our confidence interval, we take our sample mean and add the margin of error. And we end up with 146.067 or $146.07. So these are our confidence intervals. With this sample mean, we're 95% confident that the true population mean falls between $117.93 and $146.07. So if we drew these values, let's blue them out up here. This is mean for group 1, mean for group 2, 117.93 and 146.07. Here our sample mean was 132. Here our sample mean was 129.20. Keep in mind, these values are both the same distance away from the mean as these values are from this mean. It's just that this mean is slightly higher, so all the values in our confidence interval are slightly higher. This means slightly lower, so the values in our confidence interval are slightly lower. Okay, now let's go ahead and do the retro pizza example. This one's kind of tough because you have to calculate the sample mean on your own. So this is going all the way back to looking at measures of central tendency. So that may have been a challenge for you, but let's go ahead and work through the whole problem. All right. So the first thing that I want to know is my z-score based on my alpha level. And my alpha level is equal to, and we've already done this, but I'm going to do it again, 1 minus my 95% confidence interval divided by 100, which becomes 1 minus 0.95, which is 0.05 for alpha. So we take that alpha level, we divide it by 2, and we know we're looking for 0.025 in the tail. And when we find 0.025 in the tail, we already know that we come up with a z-score of 1.96. So that is our z for an alpha level of 0.05. So now we find our margin of error, which is equal to the z value with an alpha of 0.05 that has a confidence level of 95% times the standard error. So this would be 1.96 times, I don't know, right? Got to find my standard error, which is equal to the standard deviation divided by the square root of the sample size. My standard deviation is 5. And then my sample size was, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, square root of 10. This becomes 5 divided by 3.162, and we have a standard error of 1.581. So now I can plug that into here. 1.581. And 1.96 times 1.581 gives me a margin of error of 3.099. So our margin of error is 3.099. All right, before we can find our confidence interval, we need to figure out what our sample mean is. So sum of x divided by n. So our sum of x, we can simply add up all of these dollar figures. So I didn't really go into the context of this problem because I'm expecting that you've already done it. But essentially, we're looking at a random sample of 10 drivers. How much tip money have you collected in the past hour? Each one of those numbers represents one of the drivers and how much tip money they collected in the past hour. All right. So 20 plus 15 plus 18 plus 30 plus 10 plus 9 plus 30 plus 20 plus 11 plus 16 divided by 10. So this becomes 179 divided by 10, and you get 17.9 for your sample mean. So now we can find our confidence interval. Confidence interval is equal to the sample mean plus or minus the margin of error, which is saying our sample mean 17.9 plus or minus our margin of error 3.099. So to find our lower limit of our confidence interval, we can take our sample mean, subtract our margin of error, and 17.9 minus 3.099 is equal to 14.801, or, because we're talking about dollars, $14.80. And let's make that more clear because I think my dollar sign and my 1 got kind of smooshied. 14.80. All right. Then the upper limit of our confidence interval, 17.9, our sample mean, plus our margin of error. And we end up with 20.099. Or we could say, well, let's round it to 21 actually. It'd be $21. That is our 95% confidence interval. And remember, the question at hand was looking to see if we think that the population of drivers, if we could be 95% confident that the population of drivers, based on the sample, make at least minimum wage. Well, minimum wage doesn't fall in this confidence interval, and in this case, that's desirable, right? We don't want it to be there because we're hoping that they make more than minimum wage. So, we are 95% confident that Metro Pizza drivers make between $14.80 and $21 per hour in tips. So, we're 95% confident that drivers are making more than $8.25 per hour in tips. Now, this may seem compelling. You may be confident that, yeah, they're making more than minimum wage. We don't have to worry about legal implications. But the sample size is pretty small, and the manager only looked at one day. So maybe these drivers get exceptionally large tips, or the data was collected on a special day when tips are higher, like Christmas Eve. So just pointing that out so that you remember, as always, our predictions are only as good as the data that's used to make them. So I hope you're feeling pretty confident about your ability to compute confidence intervals. There was totally no pun intended in that. And I hope these examples were useful and that you tried these problems on your own and you got them correct.